Hello everyone, welcome to my video. In this video, we will look at fixed axis rotation. Previously, when we were talking about fixed axis rotation in chapter 5, we made these observations as shown here. All points on a rotational body rotates with respect to the rotational axis, and all points or lines on the body have the same angular velocity omega and the same angular acceleration alpha. And we talked about this in chapter 5. If you need a review, please review the necessary material as needed. Let's start with the two governing equations again that we were talking about in the previous video. For rotational motions, we'll modify the sum of force equation a bit, since using the NT coordinate system is usually the easiest way to analyze rotations. So we will have the rotation with some rotation axis O, the sum of Fn, sum of Ft, and the sum of Mo. The sum of the normal forces is mr omega squared, and sum of tangential forces can be written as mr alpha, and the sum of all moments with O is I alpha plus m ATR. Note it's AT here, not AN here, because it's rotating. Right? Rotating is on the tangential direction. Looking at the kinetic diagram here, we still have three equations to solve. The n direction, the t direction, and the moment, just like the xy coordinate system, right? Except we have n and t versus x and y. We discussed three basic ways to calculate the mass moment of inertia in the last video, lecture 27, as well as how to read this table to get the mass moment of inertia for some common shapes. I will not repeat myself here, just to give you a reminder that you need to know how to read this table. Guaranteed you have to know this. For rotational motions, we looked at a special point in the past called the instantaneous center of zero velocity. Here on rigid body that is doing fixed axis rotation, we have another unique point called the center of percussion. The uniqueness about this point is the center of percussion Q's location is depending on O. As you can see in the diagram, the small q, the distance, is given by the equation, and all resultant external forces must pass through this special point Q, center of percussion. In other words, the sum of moments of all forces about Q is zero, because all forces has to go through that point. So this gives us the sum of MQ equals zero. This is just how it is defined. From the reality perspective, this is if a force is applied at Q perpendicular to this OQ in the diagram. The reaction force at O, the rotational axis, where O is zero. In tools like baseball bat or hammer, hitting the object at this point Q makes your hand grabbing at O feels smooth, or just feels very comfortable, with no reaction at this hand, because if you hit something at Q, the reaction force at O should be zero. On the next slide, there is a nice video that I'm borrowing from another YouTuber who demonstrated this feel nothing concept in your hand very nicely.
When you strike something with a rigid body like this bat, there's rotational and translational motion occurring at the pivot. There's a special spot called the center of percussion where you can hit that both of those motions cancel each other out. For a bat, it's called the sweet spot of a bat. To demonstrate this, we have a bat that is being rotated by a pivot point that's a pencil. So if the pencil experiences large forces, it'll break. First, we're going to do it at the center of percussion, and the pencil is perfectly fine. This is why you want to swing a bat and hit the ball at that sweet spot, because you're not going to feel large forces and it's not going to hurt your hands. Now, we're going to try it beyond the center of percussion. And you can see now the pencil has broken. And that's because we're beyond the center of percussion, we're experiencing large forces. Physics is pretty fun.
And this concludes our section 6.4. Please take a look at those sample problems. Thanks for watching. I'll see you next time.